Excellent. It's 45 o'clock, and it's time for us to open our session two. In the first session, there are four speakers to deliver excellent presentation about AI driven network. In section two, I chair this session, and I'm Li Jingjing. I'm the director of the CSNet, China Science and Technology Network, and I come from China, Beijing, and I welcome all of you to this meeting and participate this section. There are also four presentation in this session. The first one is from Ms. Statis Kumar Panner and Lin Chan Chou. They're from University of Malaysia, and their presentation. The name of the presentation is optimizing traffic engineering in SDN through hybrid traffic forecasting and threshold adaptation. And welcome, Ms. Satis. Please deliver your presentation. Okay, thank you. And you can share the screen of your computer.
Yeah, sure. Thank you. Okay, can you see my screen?
No, I look for the help of the secretary. Okay, it's okay.
Okay, thank you.
Thank you.
Okay, first of all, welcome and thank you all for joining. So today I will be presenting our work on optimizing traffic engineering in software-defined networking using hybrid forecasting and adaptive threshold. This research was conducted at the University of Malaya in Malaysia with the collaboration with my supervisor, Dr. Ling Tek Chow. So our solution named Flownetic basically addresses key limitation in the current existing traffic engineering approaches in software-defined networking. We also tried to integrate some machine learning and statistical methods to actually predict and manage the network load proactively. So let's begin with the background. So traffic engineering in SDN or software-defined networking traditionally relies on the reactive routing, which is the default in almost all the SDN environment. So this actually can lead to congestion, latency spikes, and degraded quality of service or QoS during some unpredictable traffic burst in certain situations. So existing machine learning solution often lack some interoperability, while also purely statistical models might miss short-term anomalies. So after analyzing and studied these limitations in the current SDN environment, we tried to combine this gap in adaptive and interoperable and also accurate forecasting mechanism. So our work is basically tries to bridge the gap by using a hybrid and proactive approach in a software-defined networking to improve the current traffic engineering mechanism. So what are the current limitation in the current traffic engineering? So current SDN routing decisions are often made only after the congestion has occurred, which is too late. So this one is considered as a reactive routing. For example, the rerouting in a traditional environment is typically triggered only when, for example, a link utilization reaches 100% or when there is a link failure occurred. And this information is carried over to the SDN controller, which will then only will take any necessary action. So this kind of action would be too late because some of the user might face some consequences in connection drops and may be unable to send data or receive traffic. So in order to overcome this issue, we also sometimes would see that network administrator could fix the threshold amount like 80%, which could be too rigid for dynamic traffic patterns, because the traffic patterns in a networking environment is very difficult to actually predict. So we cannot simply set a link utilization at a static level to actually control any congestion. Moreover, the absence of the reliable forecasting mechanism in most systems also could lead to some missed opportunities to avoid future congestion. Even though we are able to overcome some of the current congestion, we are also cannot make sure of if there is a congestion in the future, that our SDN controller or our current setup could actually react to it before it could happen. So this limitation is collectively reduce the effectiveness of the existing traffic engineering methods. So in order to overcome this limitation, we propose a Flownetic, which is a proactive traffic engineering system that combines the statistical and deep learning methods. So our hot winters plus gated recurrent unit engine can able to achieve 97% of the accuracy, even with 20% of data loss in the traffic prediction mechanism. Also, rerouting decisions are also made in less than 50 milliseconds, which improve latency by 28%. So this comparison is actually made with the current baseline or the standard routing engines that exist in most of the SDN environment. Together with this, we also try to employ estimated moving average to actually handle some of the missing metrics with minimal overhead. So this is our system architecture of our solution, Flownetic. So it starts from the real-time data collection in the data plane layer, and then the flows into our prediction modules before it reaches the routing engine. So in our system architecture, we begin with data collection in the data plane layer by using some collector. In our case, we used the SFlow RT collector, which will collect all the real-time metrics from the data plane layer, for example, like link utilization, the number of switches, number of links, and etc. And then all this data will be and then sent to another tools called Telegraph, which will help in scrapping and cleaning up all the data so that only the useful data will be taken into consideration and will be stored in the database. So after the data is cleaned up and stored in the database, and then the data will be used by the traffic prediction module, and together with other modules, which I will explain later, which is called threshold analyzer and also routing engine, which will making use of this data to actually predict the traffic in our networking environment and make necessary decision and fit into the routing engine before this decision is applied by our SDN controller and making the changes in the data plane layer. So here's a closer look at how our traffic is actually predicted in Flownetic. We first apply a hot winters algorithm to capture any periodic trend like daily or weekly usage cycles in the networking environment. And then the gated recurrent unit, which is a deep learning model, it will help to correct for any anomalies that the statistical model might miss in the first stage of prediction. So this hybrid approach actually ensure that both accuracy and robustness, because even though in the first round we could miss some of the anomalies, but in the second round, with the help of the GRU, it can actually able to get rid of most of the anomalies to achieve a higher accuracy. So with the help of both hot winter forecast and then the GRU correction, the output will be combined and will be fit into routing engine, which will influence any routing decision by the SDN controller in our data plane layer. And then we also employ a new mechanism called adaptive threshold mechanism. So Flownetic actually uses this mechanism based on moving averages and also standard deviations. So the formula, as I shown here, threshold equals to moving average plus k times SD, which is a standard deviation. It allows flexibility via a sensitivity factor of k, which can be tuned depending on the network aggressiveness by the network administrator. For example, like for short traffic spikes, traffic spikes, like those which will only remain for less than 1 second or few seconds, usually will be ignored to actually prevent any unnecessary routing. Because in some networking condition, we could see a higher amount of traffic spikes, which could only remain for less than 1 second, which we consider as an anomaly. So in this kind of situation, we can actually tune the k value to influence how often the routing engine will make a decision in rerouting the traffic to alternative paths. Our implementation actually includes mainly 3 key modules. The first one is data collection. The second one is traffic prediction, and the third one is routing engine. So in the data collection module, we uses some tools like the ESPRO-RT, Telegraph, and the InfluxDB for the real-time metrics and storage, as I mentioned earlier. And then the second one is for the traffic prediction. We use hot winter and also GRU to capture and predict any seasonal trend in the networking environment, whether it's daily, weekly, or monthly, while GRU, which will handle any anomaly missed by the hot winters in the first round of prediction. And then the third one is routing engine. So routing decisions are usually enforced in ONOS by using open flow messages, because we use OVS switches in our data plane layer. But also, we able to make most of the decision and able to keep the latency under 50 milliseconds for any rerouting condition. So the system also able to support more than 200 flows with improved system delay, which I will show in the next slide. So in the results section, we will be first go through the latency reduction on how our system are able to reduce the latency. So in this first experiment, we evaluated the latency whenever there is a high load condition. We tried to simulate 200 concurrent flows where the baseline latency peaked at 140 seconds, while our solution able to reduce this to 100 milliseconds. So this is considered a 28% of improvement. So this proactive routing based on the prediction is actually effective, because even though it's a 28% of improvement, this could is actually important in certain traffic condition where some voice traffic or real-time gaming are actually involved. So in that kind of situation, latency reduction is actually considered important for real-time applications. So in terms of load distribution, here we see a throughput distribution across all the network links in our networks. So in the baseline, we can see that which is in the blue line, we can see some links peaked at more than 72 Mbps, while others are underused at almost less than 30 Mbps. So, but after we apply our solution, Flownetic, we are able to flatten this curve by reducing the peak throughput usage by each link in the network by less than 40 Mbps per second. So by making the link utilization optimal across all the link, we can actually reduce the risk of any congestion in the future when there is a new traffic by new users try to search, or some spikes happen in any time soon. So for the congestion avoidance, here we shows that Phronetic able to avoid congestion by acting early in the baseline, as highlighted by in the red line. When the utilization spikes to 100% by introducing some spikes, we can see that traffic packet loss begins to happens at t equals to 4, and it only reduced back to 0 only at t equals to 12 and 13. But by applying our solution, we're able to keep the link utilization always below 80% throughout the search alive in our network. So this actually shows the benefit of predictive and threshold triggered rerouting, because by keeping the utilization less than 80%, we can see that there is no packet loss is actually happen, as highlighted by blue line, which exists at y equals to 0 all the way until continuously. So the next one is adaptive rerouting. So here we show how the dynamic threshold actually guides the rerouting mechanism. For example, that for during normal fluctuations, for example, at t equals to 7 seconds and t equals to 14 seconds, where there is a spike, but actually it stays less than 1 second, is actually considered as anomalies, because this is because of our traffic prediction module, which able to predict that this kind of traffic surge only exists for few seconds. So it tried to reduce any rerouting from happening. And also when there is a sudden spike, and when there is at t equals to 25, when the traffic spike is sustained for more than a few seconds as configured, so the rerouting mechanism is actually triggered. So after the rerouting mechanism is triggered, we can see that the traffic begin to rerouted to alternative path to actually reduce the link utilization at in certain links from achieving 100%, which is cost which is actually exists in baseline rerouting. So the advantage of our system is it offers a comprehensive performance boost, as I mentioned earlier, because we're able to drop the latency by 28%. We're also able to reduce the peak throughput every link in the network by 30%. Also, we're able to reduce the congestion by predicting any congestion from happening. Also, we are also applied a hybrid forecasting model, which improved the prediction accuracy up to 97% with the help of EMA, which is the estimated moving average, which helps in when there is any data is missed, which will useful for the traffic prediction. By using EMA, we're able to predict some of the traffic which we think that suitable for the missed or the drop metrics in our network when it is carried by our data collector to the database. So in conclusion, Phronetic enhanced traffic engineering in software-defined networking with prediction-driven rerouting and adaptive threshold. We handles the challenges of delay, congestion, and also uneven load in SDN environment. Our hybrid model and smart threshold mechanism makes the SDN networks more intelligent and are also resilient. This approach is actually easy to deploy, and it able to scale well as I shown earlier, and it also can show some strong real-world potential. So future work, we also trying to extending our solution for multi-domain software-defined networking, and also try to integrate some reinforcement learning for better accuracy and also congestion avoidance. So thank you for your attention, everyone. We appreciate your interest in Flonetic in its contribution to AI-driven traffic engineering in software-defined networking.
Okay, thank you, Ms. Palmer. And any questions? I have a question, Ms. Palmer.
Yes.
You use a combined method to optimizing the traffic engineer. You combine traffic forecasting and threshold adaptation. So
Okay.
have you compared that only use traffic forecasting, use machine learning to optimizing compare with your combined method? Have you done this experience?
You mean the combination of the hot winter and the GRE? Sorry, can you repeat the question?
Have you compared other method of the optimizing the traffic engineer use machine learning, some other machine learning method to compare with your method?
Oh, yes. Okay, I understand your question. Yeah. So basically, after we implement our solution, we do compare with some of the solution already proposed by other researchers. And we also can see some improvement compared to their solution, because some of them only used either a prediction module or they used some machine learning algorithm, but they actually didn't combine the solution where by using both a prediction module and also the machine learning mechanism. We only able to compare with a few already available solution, and we are seeing some improvement as well. Yes.
Okay, thank you. Thank you very much, Ms. Palmer. And let's welcome the next speaker, Mr. Kim Jong-hun, who is the principal architecture of the Cisco system, and the lecture is Image AI Ops for Intelligent Monitoring. Okay, welcome, Mr. Kim Jong-hun. Hello.
Okay. Can you hear me?
Yeah, we can hear you.
Okay.
We can see your monitor. Okay.
Okay.
Let's speak. Okay, thank you.
Okay, thank you. Hi everyone in Hong Kong. My name is John from Seoul. I'm a principal architect at Cisco. First of all, thank you for inviting this meeting and giving the chance to presentation. Let me introduce my career before the sessions. Before joining Cisco, I worked at the two major telecom companies in Korea. I operated the backbone network at Korea Telecom and the risk manager at SK Telecom. In those companies, developing the observability are important part of the job. So I always dreamed the AOps then, but it ended up when the emergency call rang in the middle of the night. But now we are living in the AI era, and I have the opportunity to explore the AOps again here. So I believe it's time for us to redesign AOps for the modernized infrastructure. So today, I'd like to share the few thoughts during this session. This mainly focus on the field experience and the use cases, so it may differ from the technical sessions before. However, I hope this help you get some insight. First of all, I'd like to talk about the few common challenges in operating the modernized infrastructure. Then I'll share the experience with the previous AOps model. Based on those lessons, I'm going to show how we can redefine the AOps that we can expect to better support operations. And finally, I will show you some example of our AOps prototype. Okay, let's talk about the challenges we faced in operation today. I have been operating network for a long time, especially mobile network, where the many application is running. Back then, my KPI was clear, detecting issues within 2 minutes and recover the service within the 20 minutes. That was more than 10 years ago, based on the SLA and the customer complaint ratios. Even now, the NetOps teams followed similar KPIs. During the incident, they are expected to prove the transparency of the network and isolate the port or clearly identify the root cause. But as infrastructure became virtualized, it got much harder. The monitoring using just SNMP and CISRO no longer gives us the enough visibility. So vendors and software companies introduce analytic tools that promise smarter insight and faster resolution, but in the reality, there are barriers like language, local behavior, and unfamiliar tools. Because of those, many operators fall back on the legacy method, even if they want to change. In addition to these challenges, there is another common patterns we often see. When a critical incident occurs, another NMS was added. Eventually, the number of tools keeps growing, and so does the complexity. In my cases, I have to monitor the 108 different NMS. So we jokingly call it 108 agonists. In China, 5 are fun now in Buddhist, because it really felt like a burden. So many systems meant more alert, more silos, and more chance to miss something important. The second issue is about the people. As you know, the operating network rely heavily on the experienced engineers, but due to the company-wide HR policies, many senior experts have retired or moved on. At the same time, junior engineers often faced a steep learning curve. They ended up switching teams or joining cloud company instead. So now we face the serious skill shortage in the operational field. Of course, in this environment, many teams consider automation or the SRE engineering. But here is the challenge. When an incident happens, a wrong decision can impact not just the service, but also the business, and sometimes even careers of leadership. Yes, that means they can lose the job of our leadership team. That's why many teams stick with the traditional decision-making processes, even though their infrastructure is already modernized. That's why we need the AOps to bring the all signals together and find the root cause faster. So let's see the AOps model. You may think AOps will be based on the generative AI, but if you look at the Gartner's definition when it first came out, it's a platform that uses the big data and the machine learning to improve the IT operations. In my experience, I had a chance to lead the AOps initiative for the telecom company. We used the big data to consolidate the insight across all layers from the mobile network to the applications. Can you guess how much we did cost? It's over $60 million. Yes, it is too expensive for the most companies. Later, when I joined the Samsung as a project manager for the e-commerce platform, I began to exploring the startup in Silicon Valley. Many of them were building the AIOps solutions using the machine learning. They often claimed the success, but in the reality, I rarely met anyone actually using the AIOps in the field. Why? Let me show some reason. The first of all, when AIOps came out, the machine learning and blockchain were the hot topics. So at that time, all employees in my company should run the machine learning. The operational team needed to consider use case first for the AIOps, but the data scientists checked where to use the machine learning. Hence, applying the machine learning was not successful at that time. The second, after introducing AIOps model, the many team complained that things didn't actually get better because AIOps often doesn't give the answer operators really need. It just gives them more tasks based on some rule sets. So we create the garbage in, garbage out. Even with the generative AI, it's the same. If the data is wrong, you can see it is just get colorful garbage, and it only makes things harder for the operators. Finally, let's look at the gap between the stakeholders. AIOps reminds me of the autonomous driving. We have a definition up to the level 5. In practice, as a level 4, the Waymo is the driverless taxi running in the United States. It looks unusual with all cameras sensors outside. Like most automobile companies, the Mercedes has reached level 3. It is still great. By the way, can you guess the brand of the first one? It's Bentley. And the Bentley announced last year they want to pursue the autonomous driving. But I have another questions. Which car would you choose? The white one, fully autonomous with the camera and the sensor outside, or black one without the autonomous driving at all? Just like that, there is a gap between the machine learning expert and what operators really need. I wonder those reasons make sense. Maybe you can find a similar insight in the one I did report that shows real-world AIOps experience in advice. Because many AIOps tools were developed by the machine learning expert, they focus on more than data and performance than operational use cases. And since they lack of the field experience, it wasn't easy for operators to share your operational context with them. The report emphasized that the one key lesson was to clearly define who the user of the AIOps are, and develop within the right scope and based on the actual operational needs. It also advised that what matters more is that choosing the tools and vendors that offer enough relevant use cases, not just the fancy algorithm. From the lesson learned before, we developed a new definition. It's teaming with AI. In other words, rather than giving the homework, AIOps is the model that provides operational teams with insightful data that accelerated them to make decisions. For this, we need to collect more data and reuse the machine learning to detect the anomalies and reduce noise and analyze the event correlations, but the optimized way. And we can leverage the generative AI to develop the user interface more easily. So when you look at the AIOps AI assistant part, the user interface has also changed a lot. At first, we checked the switch using the CLI command. For the past 10 years, we have been checking and configuring by a UI in the controller. But now, because so many clicks frustrated operators, they retrieve data and automate the workflow task through the API. Now we released the AI assistant model to cover these operations, especially campus network and security. But there's something I have not mentioned yet. Most of the AI assistant model are SaaS-based. You should connect to the internet and often rely on the external data sharing and the continuous learning. It's not easy to share the data, and the customer cannot wait for the long time to train. So here's the real questions. Is it possible to build the AOps in the on-premise and still delivers value in a short time? So let me show you what I have done answering these questions. I follow the advice in the IDC report and interview the key customers across the different industry and show a few examples. The first, semiconductor company, they have multiple factories across the region and where IT and OT were deployed integrated. Over the time, the environment became highly complex with multi-vendor and aging devices. Because of the scale, it was difficult to fully control what was happening remote side. In one cases, the connecting power monitoring device caused the unknown issues that impacted the production, so they had to discard all wafers in processing. It resulted the business loss. They estimated the 1 minute outage can lose the $3 million in the factory. So this customer wanted to sense the fault point in real time and they need automated resolution for critical issues. Next one is the e-commerce company. They are currently number one delivering platform in Korea, the famous for the rocket delivery. As their business grew, they rapidly built more warehouses, and network became mission critical, but the number of the operators did not increase. Now, one person should manage over the 3,000 devices at the same time. So they asked for the AI assistant model to upload the daily operation task like a flow-based analysis, service insight, and daily system checks. Last one is bank. Their network was relatively simple, but they lacked skilled engineers. So they had to respond to urgent requests from the application and server teams. This sometimes led to human errors. The more than the outage itself, the biggest concern was the regulatory reporting to the financial authorities. So they wanted a way to analyze the massive logs during the incidents and feel confident rebooting a device remotely. They also requested chat-based support for configuration and guide due to the limited operator experience and the language barrier. As you can see, each situation is a little bit different, but the core needs is similar. All customers prioritize the business impact and wanted a fast analysis and resolution based on the use cases. And instead of the full automation by AI, the most preferred the AI assistant model that support operators, not replace them. So getting insight from these use cases, we also categorize the use cases into the two types, the defined and undefined scenarios. The defined scenarios, such as identifying the fault domain or conducting pro user basis analysis, as you see, we can standardize the detecting and the resolving procedures. The key is to reduce the detection time and minimize the human error. Since operators have different skill levels, we need to optimize the process accordingly. For less experienced operators, an AI assistant can help them access the insight easily. This way, AOps can constantly reduce the MTTD and the MTTR, regardless of who is using it. Now let's talk about the undefined scenarios. And there are typically two situations. First one is the two main logs, and the other case is the no log at all. When there are two main logs, AOPS need to filter them using the rules and then correlate the event to identify the root cause. In these cases, rank model can be used within the vector databases, leveraging the documented data like white papers and logo manuals from the vendors. On the other hand, when logs are insufficient, we need other type of the data from the network. That's where the telemetry or the TWAMP can help. These tools collect the performance data from the devices, and with this, AOPS can estimate the fault domain based on the telemetry, allowing the operators to validate the performance via dashboard and make data-driven decisions and take the proven actions. So we cover all scenarios, but I'm going to take the defined scenarios at this moment. So defined scenarios, we can design the solution using the three main components. The first one is a controller or the machine learning-based analytics platform to collect the data and having insight. Second is the unified observability provides a dashboard by domain owner. The last one is that AI assistant to improve the usability and provide the quick insight. Today, network can collect the real-time data through the controllers and analytics tools. And this approach works not only the data center, but also the backbone and access networks. A unified observability provides dashboard tailored to what each operators need. It can be built with tools like Elastic or the Telegraph Stack, and we can use the Splunk, which most customers have one for the security. And by adding the AI assistant, we can make it even easier for operators to gain insight quickly, act with confidence. And we can implement the AOPS workflow like this. The first, we need to design the workflow based on the decision-making process for the operational team. We can automate the standardized analysis steps using the MCP server. So manual operation action can now handled automatically. The LLM model plays a supporting role, like the helping understand the user request, guiding configurations, and even supporting multiple languages. However, if we want to preserve the decision-making process, we must ensure that evidence can be easily shared and understood with other stakeholders, including the leadership. Text is not enough. So the various type of the output, such as image, document, or double check through the link is needed. But during the investigations, we found that some MCP hosts don't support file-based output, which made it harder to share the clear evidence via UI. So in such cases, a collaboration tool like Slack or WebEx might be better because it is one of the operators' communication tool and support multiple types of the outputs. And as you see the middle of the diagram, we also define the key use cases by the output and develop them on the MCP-based server. The solution remained usable even if the LLM model is later replaced or expanded. So let's see a quick demo from my laptops. As you see, this is the WebEx space is one of the collaboration to the operators and Cisco employees. It looks like the chatbot, but inside there are the LLM and the MCP server is running. So I can the greetings to my assistants like hi. Yeah. She answered. And then we can ask some different languages. Yeah. necessary? And she answered the Chinese, because it is running on the LL model. So let me ask some pros. If you capture the pros in the network, we use the protocol or some devices to capture traffic, but it is the defined scenarios. We can set up the before the asking. So it provides some capture the image from the analysis like that. And it also provides the CSV file, including the detailed flow data like the source IP and destination IP and its delay or the latency. Yeah, everything is inside in the CSV file. So we don't need to set up some computation to capture the traffic. I can ask the other questions. So show me the host. So the AI assistant acknowledged the request, and it provided it provided the capture the image of the dashboard like this, and we also check the link and access the dashboard. Actually, I developed the dashboard using the Splunk, so you can see the host, the status, and traffic flow and loss by the host, and location as well, and the detailed the flow informations by the host. Maybe you can understand it is written by Korea, but we also have the English version. Like this. The reason why I choose the Splunk, it is easily can translate to the other languages. The same output here, and I can also ask the detailed specific informations like this. Then the existed the analytics tool can provide the flow informations with the detail. So as you see, it provided detailed informations. Detailed informations about the flow, and also provide the path that host the path to which switches to get the destinations. So this AI assistant is work for me, but in the real world, we have the team spaces to share the informations. So for example, there are the AOps team spaces, and we have some message from the CEO. He have some issues, and he is very upset. So let me. So in these spaces, I call the AI assistant and show us the VIP status. And the AI assistant can check my request and show some kind of this informations. Let me access the dashboard. So I translate to the English version, and you can see the VIP status in my network. We already monitor the CEO and the CFO the status in the network, so we don't have to troubleshoot or analyze after finding his IP addresses, because we can by doing that, we can reduce the MTTD and the MTTR eventually. And normally, but we want some anomalies in the network. If I went to the office and we check the daily check, so we can ask like that. So I asked using the Chinese word, and it can easily understand what I said, and it shows the same CSV file containing the anomalies for the one day. So there are many anomalies here, and then you can see the microburst and traffic issues and interface status, and you can see the buffer drop, and we don't need to develop some kind of the rule set to detect that kind of issue, because we can use the analytic tools for that. Just we can simplify the access and detect this kind of the anomalies. So let me return to my text. This kind of model is maybe it became popular because we also introduced AI canvas model in the Cisco Lab last month. It demonstrated almost the same behaviors and use cases. And I believe that's natural, because most of these ideas are directly inspired by real-world operational needs. So let me conclude these sessions. A new operational approach is needed for the modernized infrastructure in AI era, and AOps is evolving into the role that helps operators make quick decisions. And if you adopt AOps, I suggest step-by-step approach aligned with the business goal and use cases. Okay, that's all I have to for these sessions, and thank you for the listening today. And do you have any questions? Please feel free to ask questions.
Any questions? I have a question, Ms. King. As you know, that AOps is a very useful tools to run a huge infrastructure of the IT, and we think that the key role of the AOps success is the quality of the data to feed up the machine model for the AOps. So my question is how to improve the quality of data to feed up the model when we training the model for AOps. Thank you.
Thank you for the questions. As I said before, we can separate the model by the scenarios. For the defined scenarios, we can easily develop, or we can easily improve the quality when we develop the more use cases. Maybe it covered all of the operation behaviors. But on the other hand, undefined use cases, to improve its quality, we need to input more data to the LLM models. Yeah, that is the issue, because there are some gap in the field from the customer, because we have the difference of the quantity of the data from the vendor and the customer side. So in these cases, someday the AOps is the normal. Maybe the vendor can provide some data for the customers for improving the AOps model. But currently, I think this is just the first stage. Maybe the customer can collaborate with the vendors to improving the AOps models. But for the quantity of data, we need to think about how we optimize the data. We should not input all data from the network to the LLM model because, there are maybe the 90% of the data is not good. So currently, I'm considering how to optimize the data, and we can make the useful data from the old data.
Okay, thank you. Thank you very much, Mr. Kim. And I am glad to introduce the third speaker, Dr. Mohammed Ibrahim, who is from University of Haripur from Pakistan. The title of the lecture is Deadline Award Task Scheduling for Delay-Sensitive IoT application in edge computing. Let's welcome Dr. Mohammed.
Hi, hello everyone. Is my
Uh,
voice clear to everyone?
Yes, I can hear you there, but we can see the monitor sharing.
Presentation, may I share the presentation?
Uh,
Is my presentation visible?
Okay, we see that. Okay, let's begin. Thank you.
May I start?
You can. Thank you.
Okay, thank you. Thank you very much, first of all, for giving me a chance to present my work in a prestigious conference that you have arranged. It's a very good initiative because it will provide some opportunity to understand what is currently going on. We learned a lot from this conference. One suggestion for future is that we should also utilize this event for future collaboration. So that we can have some practical collaboration. Okay, today the topic of my presentation is basically the work we have done on the task scheduling in the case of fog and edge computing. In some cases we call it fog computing, in other cases we can call it edge computing. So basically the main objective of this work was basically to find the most suitable scheduling mapping so that maximum of the tasks get the deadline acceptance while also the load is balanced on each node, because if the load is not balanced on each devices, then it can lead to large execution time as well as resource wastage. So to improve the resource utilization is one of the objective, which is basically concerned with the service provider. And the second one is the deadline, because every user is interested in deadline, so that the deadline of his task is met, deadline of his application is met. So if the deadline of application it means the user will be happy, and also the service provider can be happy. Okay, we already know the IoT devices are generating a lot of data, and that data need to be fed into the cloud, maybe edge, and so on. And some of those IoT application, they may have some like normal requirements, but some other IoT application they need to have like a very stringent requirements in terms of delay. They need some solution which can guarantee the delay. And cloud computing, which is basically already providing the solutions for many of the IoT applications, but problem is that cloud having some issues related to the delay, because the communication delay can be very high in some cases. So it means in many cases, in many of the IoT applications which required a very real-time response, cloud computing will not be an optimal solution. Fog computing is basically fog and edge computing is basically providing a solution so that the 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 processing power can be given at the edge, and devices can be scheduled, can be executed in a real time or near to real time. So fog computing give you the platform where you can schedule it. Some urgent tasks which are required like string and delay requirements, they will be scheduled on the fog nodes, and some other devices we don't need some very strict delay, and they required some high processing power, so in that case they can be scheduled on the cloud. Oh, the problem is that we have the fog, which provide a way to like locally execute the task, but there are some other problem. For example, the problem is that how you schedule, how you select the device, because selecting device is one of the most important tasks for a certain task, because if there are some in a heterogeneous environment, the devices can have different hardware requirements, and the tasks also are heterogeneous, so in that case they will require some different level of service. So we need some scheduling mechanism that will intelligently map the task while meeting some of their requirements in terms of delay, response time, task scheduling, and some resource constraints, keeping in view the resource constraint. Some key challenges, like we need achieving the load balance scheduling that will minimizing the average response time, because the users are interested in time, so we need some average response time which will be better. And also the resources need to be efficiently utilized, so for that case we also need some way, some mechanism, some scheduling algorithm that will basically meet the demands of those delay critical application, and also to usefully utilize the devices, the fog node devices, because those resources are scarce, and we need to efficiently utilize those resources. So if we don't do it, which is currently involved in some of the solutions that even are giving, but there are some other problems later on we will discuss. If we don't if we schedule the tasks on the devices without keeping the load balancing, what it will cause, it will lead to some overutilization or underutilization. Maybe some devices which are basically having high processing, they may have all the tasks with them, they will schedule it, and that will lead to overutilization. And also some underutilization. In some cases some of the devices will didn't get the task to be scheduled. Previously, some of the approaches they solve the solution, like they dealt with the delay critical applications, but they didn't consider the load balancing, because load balancing is important. Even though delay awareness, delay deadline critical application, handling delay critical application, deadline critical application is important, but on the other hand the resources are scarce, so we need some mechanism that will efficiently utilize. And for efficient utilization, we need a load balanced task scheduling. So basically, in this research, we have proposed a scheduling mechanism that will select the best node regarding the criticality of the deadline, and as well as it will consider the load balancing. So it means if we consider both of those parameter, what it will lead to meet the deadline of those application, as well as to improve the resource utilization. Here are the details of some of the work which has already been done, like some of the approaches we can see they focus on the deadline, and they consider like some of the metrics like response time, processing speed, and processing time. So what we considered, keeping in view the research gap, we proposed a scheduling algorithm that basically lead to an improved task scheduling, that on one hand meeting the deadlines of most of the deadline critical applications, as well as to improve the resource utilization by scheduling the task in a load balanced way. We already meant that some of the approaches are basically met some one of the objectives, but we focus in this multi-objective approach which efficiently utilize those resources. This is the system architecture of system model of our proposed technique. The top layer is the user task layer, with the user generate task, user give task to the edge layer, and the IoT layer is basically providing the data, which is gathering the different devices data, and IoT application get data from the user, and the scheduling done is in the fog layer. We have different components on the fog and edge layer, that are service manager, resource management, load balancing, task mapper, task dispatcher, scheduler, fog broker, device management, and fog DB management. The core component of this approach are basically the fog broker and the task scheduler, as well as the load balancer. So the responsibility of the fog broker is to basically assign the task based on the provisioning by the task scheduler, and the task scheduler basically keeping in view the deadline requirements of the task, they get the demands, and based on the available devices, it finds the optimal device which can calculate the which can basically find which can fast basically find the device which can meet the deadline requirements. And what the load balancing module does for you is that while scheduling, it also considers the load balancing. So if for example, if we find a solution which basically meet the deadline of the applications, but if the load is not balanced, so load balancer will balance the load on different nodes and reassign some of the nodes, some of the tasks to the underutilized nodes, so that scheduling can be done in an efficient way. These are basically the two scheduling algorithms, which are basically scheduling as well as the load balancing. So the first sub scheduler, what it does for you is that basically it finds the best optimal devices, best optimal devices which deals to deadline critical application. And the second sub scheduler is that it does perform two tasks, rather three tasks. First is that if some of the tasks misses the deadline, so it will basically reassign nodes. It will find other nodes, some nodes in parallel, so that they can execute in keeping in with the deadline requirements. And the second objective of this algorithm is to reassign the nodes if the load is imbalanced on the different tasks. So schedule enable will select the fog node that will have minimum completion time under the deadline and load constraints. So it will, keeping in view the deadline, it will first find the minimum completion time, and the scheduler 2 will find the alternative placement if some of the task the deadline of the task is missed. And also it finds the most suitable mapping that have minimum load imbalance as well as to meet the deadline of most of the tasks. So what it does, it first calculate the load threshold and select the eligible nodes and assign nodes to that time. That will minimize the completion time and as well as balance the load to meet the needs of the task. And then update the task in node statics. That is like the in terms of implementation that the tasks are basically mapped, assigned, and stored in a table, hash table. uh, scheduler 2 is basically triggered, which when scheduler 1 will not be able to find the deadline of the requirement. And secondly, the if the load is imbalanced, it will also find the load balance. In this work, we utilize the iFox simulator, which is basically a benchmark simulator for simulating our proposed scheduling algorithm. And the fork nodes we selected is 5, 10, 15 to 30, while the task sizes are basically 50 to 300. In order to compare our proposed approach, we basically compared with 3 different approaches, that is DRAM, MPGA, FTLS BA. So we considered the different metrics that are resource utilization, average delay, task execution time, average response time, and load imbalance. The first graph that is showing the resource utilization. So if we see on the 50, for example, the resource utilization is a bit low. Why? Because this is basically like the average of different trials, different simulation we considered during the task execution. For example, in previous slide we saw we have the varying number of nodes, for example 5 to 30. So each of on for each of the task combination we considered all the different nodes combination, and then we took the average took and plotted the average results. So if we see, so while the number of the task has basically increased, so the resource utilization is improved. So one of the reason is because we most of the devices are engaged in scheduling, and second is the load balanced way scheduling, which leads to an improved resource utilization. In this graph, we see 2 different results. One is related to the average delay and execution time. So the execution time, the minimum execution time, which is considered by the proposed approach, is around about 4,000 millisecond, while the maximum utilized while the maximum time that is attained by the paper one, the paper 2, while the average delay which suffered in this case is the almost near to the execution time. These are the results regarding response time, average response time, and the average delay we already considered in previous graph. These are the load imbalance results. The proposed approach has able to minimize the load imbalance, which we can see is related almost 1%. These are some of the findings of the work. Like for example, the proposed approach improved the resource utilization by 18% over the MPGA, while delay improvement is 30% over the DRAM, 24% over the MPG, and 12% over the FTLs. The execution time is reduced by 14% for the 150 to 200 tasks, and the average response time is basically improved by 15% over the MPG and 25% over the DRAM. And similarly, over the FTLSBA, it has been able to improve the average response time by 27%, while the load imbalance reduced by 74% in case of the FTLBSA. So the conclusion of this work is that we have proposed a scheduling algorithm that improve the deadline requirements of the delay critical application, and on the other hand we also improve the load imbalance for the task scheduling. Any question?
Okay, thank you. Any question? Dr. Ibrahim, my question is, we saw that there are two approaches to improve your algorithm, including resource aware and deadline sensitive. My question is, which is more important in your algorithm? Those two.
More important is basically the deadline. Deadline is important,
Okay.
yes.
Okay,
So
thank
for
you.
that we consider the delay.
Okay, thank you. Thank you very much. Okay, let's introduce the final speaker to deliver the lecture. Title is Resource Management in Sagin, Port Orchestrated Task Offloading and Density Aware SDN Controller Placement in Neo Satellite Network. Let's welcome Mr. Umar Mahmoud, which is from Jeju National University in Korea. Thank you. Okay, you can start your lecture, Ms. Umar. Thank you. We can see your slides. Let's begin.
Good morning, everyone. Can you hear me? Hello. Can you hear me?
Yes, we can.
Okay. Good morning, everyone. My name is Umar Mahmood, and today I will present two works related to resource management in Sajin. First is SDN controller placement in new network satellites. And second is intelligent task offloading using a dual cluster Kubernetes framework. So first of all, this is the flow of my presentation. I will start with the motivation and background, introducing Sajin and explaining our two contributions, SDN controller placement and intelligent control or pod task offloading, and then conclude with the key results. So first of all, the introduction, this will explain satellite networks, especially LEO constellations are designed for global coverage, enabling connectivity enabling global connectivity in remote areas. They support diverse applications, for example, IoT, emergency services, and uh, uh, broadband access, etc. The network architecture includes satellites and links between the inter-satellite links, forming a dynamic mesh. In making a dynamic mesh routing in the space architecture. So, there are some issues. But there are some issues in the architecture. For example, the satellites, they move, and sometimes they disconnect from each other, like there is a line of sight issue. And so this also introduced some of the issues in the in Sajin. Then the next is space air ground integrated network. We can say that it makes communication more reliable together with sorry, uh, so there are some connectivity challenges in the Sajin with the growing demand of IoT devices. For example, we expect over to 25 billion IoT devices by 2030. This means we need networks that are large, fast, and flexible. Secondly, terrestrial networks like cellular networks don't work well in remote or rural areas such as mountains, oceans, or disaster zones. They have coverage and scalability issue. Then third is many new services like low latency and reliable connections, which is harder to guarantee with ground networks. So we need space, air, ground integrated networks to solve these problems. So by combining all these things, Saji improves coverage, reduces delays, and support a wide range of services, including IoT, 5G, and critical communications. So then so what it does is Sajin SDN helps separate the control and data parts of the network. In Sajin, SDN controllers can be placed at each layer of the each layer, like in the space layer and air layer and the ground layer. They can manage routing, network slicing, and service quality. But when we place these controllers, where we place these controllers matters a lot. That's what we are going to solve first. So the challenges we went into for these slides for this presentation are: first is the SDN controller placement, because satellite moves and network keeps changing, so we need to choose controller locations that reduce delays and handle mobility. Second is the task offloading challenge. Sometimes ground stations can get overloaded, so we need to decide when and how to move tasks from ground to satellite. Uh, we will base our decisions on CPU, network load, and line of sight. So the first one is, in the first part, we will try to find the best place to put SDN controller. The goal is to reduce the delays and make sure the traffic is managed. So for this, we are going to use density aware methods. This means we will look into the crowded and isolated satellites. So the goal is to choose the best controller. Is we can reduce three key issues: the worst case delay, and the load imbalance, and the cluster instability. This means the worst delay is the longest time it takes from a switch to connect to a controller. The imbalance is like some of the controllers are overloaded, and some are just sitting idle. So we will look at into it. So all the load is balanced among all the controllers. Then and the cluster instability is as satellite moves, connections change. So if the controller is not placed well, the whole cluster can become unstable somehow. So to solve this issue, we used a composite score. We use a composite score that actually combines three things: how the density of the nearby satellites, and isolation distance from other satellites, and neighborhood compactness. So this formula shows that phi is the local density, like it shows how many nearby satellites are surrounded, and this delta shows uh, the isolation distance. It means that how far is the other satellite cluster, and the sigma shows the neighborhood compactness, like how tightly a cluster in the neighborhood is. So this whole thing is the combined compactness factor shows that if it's high, then it means that the satellite is well separated from other dense regions, and its neighborhood is tightly packed, and such satellites are ideal for controller candidates, and they can play a good role as a controller. So how it's done is, first of all, we calculate the distance from local density to each satellite to see how close they are to each other, and then we compute the isolation and compactness, and check if satellite is too close to others or has tightly packed neighborhood. Next, we score all the satellites using those values and select the top k as controllers. So after that, the top k satellites are selected as controllers, and all the other satellites assigned to them as their neighbor satellites or switches. So finally, we recenter the controllers to reduce the worst delay inside those groups. So for the evaluation setup, we did for the test, we used Iridium Next satellites with 66 LEO satellites. We compared our approach with three other methods: k-means, k-means plus plus, and spectral clustering. For metrics, we used average controller to controller delay and max switch to controller delay inside a cluster, and traffic distribution efficiency. So here are some of the results. So according, as you can see, that we have achieved 93% improvement in worst case delay compared to spectral clustering, and we got 18% better traffic distribution than spectral, meaning the load is more balanced across controllers. As you on and The TDE score is the highest, close to 94%, and this middle one is maximum switch to it's actually the uh, worst case delay. Then the second part of the work is task offloading in Sajin. Some nodes get overloaded and others stay idle. So in this work, we focus on how to offload tasks intelligently between ground stations and the satellites in a fast changing environment. So first we have to handle the latency sensitive tasks like IoT tasks where delays must be kept very low, but this is hard due to dynamic CPU and network loads and unstable satellite connections, like when there is a line of sight when the line of sight is lost. So there are some existing solutions but they use static scheduling or don't react on real time changes. There are some are non-intelligent offloading or migrations. And they handle satellite ground difference poorly, like mobility or resource gaps. So to bridge these gaps, we proposed a Kubernetes based dual cluster system. We simulated our network with two clusters. One is ground cluster and the satellite cluster. The ground cluster for with 12 ground stations, and satellite cluster with 33 active satellites. And the custom controller Here, the custom controller makes decisions based on the real-time values like CPU usage and network loads and line of sight. So what happens is, if the ground station is not overloaded, the task will go directly to the ground station. But if it is overloaded, then it will be scheduled to the then we will calculate which satellite to put that to offload the task to, and it will assign a pod, and it will create a pod that will form that task, and it will automatically be destroyed after the completion of task. So how this works is, with the initial scheduling, scheduling, all the tasks will be assigned to the ground station. If the CPU and network threshold is lower than the threshold. So so if but if the they are o- if ground is overloaded, and some satellites meet those requirements like low CPU and valid line of sight, then that task is not scheduled to the ground station. They are sent to the satellites. that's particular satellite, and in during those tasks, if the line of sight is lost later, we perform a pod migration to another satellite that still meets the condition. So our main objective is to minimize the total CPU and network load across all active ground and satellite nodes to keep the system fast and balanced. So these are some of the results. On the left, as you can see, the latency improved after loading. This is a ground cluster, and this is a satellite cluster. So ground cluster dropped from 120 millisecond to 80 millisecond, and in satellite cluster it dropped from 200 millisecond to 130 millisecond. And and likewise on the right side, CPU usage and network utilization before and after the offloading. So ground station loads dropped from 80% to almost 45%, and satellite load increased from 35% to 65%. So it became balanced after the offloading. Now this graph shows the trade-offs between offloading frequency and system performance. We found that best performance happen when offloading is between 40 to 60%, marked by this green zone. In this range, the task success rate is around 90%, CPU is well and balanced, and latency is low. As you can see this one. So what happens is, if we offload too little tasks like here, the ground stations become overloaded, causing higher latency and more failures. But if we offload too many tasks, it also increase the latency and the satellite stations become overloaded. So this is the sweet spot from 40% to 60% where this performs the best. In the end, the conclusion is the summary. We proposed two solutions: a density aware controller placement method, which reduced worst case delay by 93% as compared to the spectral clustering. And the second one is Kubernetes based offloading system, which improved latency by 35% and CPU balanced CPU load by 43%. So that's all from my side. If you have any questions.
Any questions? Okay, it's it's on time to finish our session. So if you have any other questions, please write email to Mr. Uma and or write to Professor Song. And thank you for all of you participate in this session offline and online. And thanks to our four speakers online today. And thanks to our chairman of this session, Professor Song. Thank you very much. Okay, it's time to finish our session, and see you next time and next event. Thank you all, and have your lunch. Yeah.